Okay, good evening, everyone, again, and welcome to week three of Fundamentals of Nano and Quantum Photonics course offered by NPTEL portal. And the course instructor is Professor Naresh K. Imani, and I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay and TU Berlin. And today, what we are going to see is that we are into week three, and we are going to cover low dimensional systems, certain things about how the absorption takes place in these low dimensional systems. We are going to talk about selection rules, which are the rules governing the transitions in, let's say, semiconductors or quantum wells, quantum dots, or these systems having different energy levels, whether mostly talking about the discrete energy systems. So this is the rough outline what we are going to cover. Uh, so what we are going to see today is let me just briefly write the outline for today's session. Okay, let me just write the outline. So for the today's session, we will be trying to cover, let's say, low dimensional semiconductors. We will be trying to cover how the absorption takes place in these low dimensional semiconductors. This will include studying about Fermi golden rule, Fermi golden rule. We will talk briefly about something like matrix elements. What is a matrix element? We will talk about density of states. We'll talk about density of states for 3D, for 2D, for 1D, and for 0D systems. Okay, and mostly we're talking about semiconductors here. Okay, we're talking about semiconductors. Then we will briefly look into certain applications where these systems are necessary. Let's say we will talk about LEDs, photo detectors, maybe lasers. Uh, that those will be the I should say the basic applications we'll be mostly dealing with. So getting started with the first of all, if we talk about the what are these low dimensional semiconductors? Let me just switch the mode and let me just try to. Okay. So first of all, what are we talking about here? So the brief outline will be I'll try to cover roughly what professor has covered in this week. That means week three. Okay. So whatever the professor has tried to cover, we will try to just revise it in 1 hour, and the this will be for the revision, and the next 1 hour will be for the question answer solving session. Okay, so that is what I will be trying to follow for this session and also for the upcoming sessions, and that is what I have been following till now. Okay, so that you can have a rough idea what was basically covered in this particular week, that is week three. Okay, so let's get started quickly. Okay, so first of all, we talk about a low dimensional system. What is a low dimensional system? Low dimensional system. So low dimensional system is, let's say we talk about a bulk system. It's like a 3D system where an electron can move in X, Y, and Z directions. Okay, so that's a 3D system. If we talk about 2D system, the classic example is something like a quantum well. It's like a quantum well. It's a two-dimensional system. Here, the electron can move in X and Y direction only. That means one of the direction electron is confined. So one direction electron is confined. So that is a two-dimensional system. Okay, so motion in two directions. So let's say for example in this the electron can go here, the electron can go here, but the electron cannot go in in this red direction. Okay, that is basically the growth direction. So if you talk about two-dimensional, how you form a 2D well, you basically deposit different layers. Let's say you have one layer here, you have another layer, surrounding it. You have another layer, let's say you have aluminum gallium arsenide on the two sides, and the blue one is gallium arsenide. So this is basically the Z direction, which is basically something called as growth direction. Growth direction. So it's the direction in which your material grows. So in that growth direction, electron cannot move. So that is why it is said to be a two-dimensional system. Okay. Now we have one more system, which is basically, let's say, for example, wire, a nanowire. A nanowire is something like, for example, you have a wire wherein the electron can only move in this direction, only in X direction. So electron can move in 1D only, but an electron is confined in 2D. Okay, so it can move only in X along Y and Z direction, it's confined. So electron cannot move in this direction. So what happens basically to the energy of the electron? That is what we are going to see. And what happens to the optical properties? What happens to the optical properties? Particularly, we are looking to for the absorption, for the absorption of the light. What happens to that if we talk about going to the low dimensional semiconductors? Then one more thing is there is something called a zero D system, which the classical example is basically a quantum dot. So it's just like a people sometimes call it like an artificial atom. Why an artificial atom? Because it is just like an atom, but you artificially make it instead of nature giving you. You can just make a quantum dot on something like gallium nitride or gallium arsenide or something like that. And here the electron is confined in 3D. Okay, so the electron cannot move at all. So if you have a, let's say, a quantum dot and you have an electron here, it cannot move in neither it can move in X nor in Y nor in Z direction. So it's totally confined. So it's totally confined in all of the directions. Okay, and why is it that necessary? Because if you confine the electron in certain system, then you can make it undergo transition and recombine with the whole to give it the light. So that is why these confined structures are basically necessary, so that your electron is confined in some localized structure like a quantum dot, and then it undergoes transition and gives off light. And this quantum dot is particularly very hot in basically it's basically used in the application called a single photon source. Single photon source is basically a source. It's like a quantum emitter. It's a quantum source. It's not a normal light source. It is a light source, but on an average, it emits only one photon. That is bizarre thing. And when you go to a one photon level, I have talked about it in the beginning that once you go to a single photon source, it's no more governed by classical laws. It's a quantum mechanical entity. Okay, and it is governed by quantum laws, obviously. And this is used in quantum information processing, quantum information processing. So that is basically the fundamental application why these low dimensional systems are also important. I'm just talking about this quantum dot. So there are quantum dot based single photon sources. Okay, let's say for example, if you have a quantum dot here and if you have a energy of a quantum dot just like this, so there might be another the hole here. So so for example, let me just show you if this is a quantum dot, its energy level will look something like this. So you have an electron here. Electron basically comes from the surrounding system, or you can inject it by applying the bias to the quantum dot. Let's say you applied a bias to the quantum dot, plus minus, then you are injecting electrons onto it, and it can basically, because of the discretized energy levels, and Pauli's exclusion, obviously. So this level can hold at max two electrons. Okay, but let's say if it has one electron, that one electron undergo recombination with the whole and gives off one photon. Okay, so that way you can exactly control how many photons it can emit. Okay, so it's a very tricky thing to make, even to work. But when you get one photon, you can basically then encode the information in let's say form of polarization of photon. Okay, so you can have, let's say for example, you can represent the information as something like 1 over root 2, the horizontally polarized photon plus vertically polarized photon. So you have the probability of half probability of having the horizontally polarized photon and half probability of having the vertically polarized photon. So it's just like a spin of an electron. A spin of an electron can be upspin, it can be it can be a downspin electron. So that is the same thing, same notion with the photon, but the information is encoded in the form of the polarizations of the photon. Okay, so this is the polarization. So this is the spin for the electron. Okay, so that way you can encode the information. Now that is the single application. Now what we are basically talking about here is, let's say for example, we talk about LEDs. LEDs also the applications they are basically made up of, let's say for example, 2D systems. Let's say for example you have aluminum gallium arsenide, you have gallium arsenide, and then you have aluminum gallium arsenide. So aluminum gallium arsenide has a higher band gap, so it has higher band gap, and gallium arsenide has a lower band gap. So when you connect these particular systems, you get a system like this, wherein now if you inject electrons into the, let's say for example, gallium arsenide, because of discretization of energy levels for the electron and the hole, you will get electron hole pair recombination, and it's going to emit the photons. So now the photons will come out. So that is basically in the, let's say, the visible region, and you can tune that those regions as well. Accordingly, you can get a photon of red, green, blue, and accordingly you can have applications in display screens. Let's say, for example, if you want to use this LED in display screens, displays, okay, then you can basically give different levels of voltages as well as currents in order to tune it according to the red, according to the green, and according to, let's say, let me just add blue, according to the RGB lighting. And if you have these primary colors, you know that you can form any of the colors. So that is how basically the displays also are made using these particular two-dimensional semiconductors. Then another application is basically if you talk about lasers. So lasers are the classical application if you have, let's say, for example, a 2D systems. If you have 2D systems, that means, let's say, for example, you have a system like this. If you have a substrate, and if you go on depositing certain layers over this substrate, okay, so let's say for example this is the growth direction, this is the growth direction, which is the z direction. And what are these layers? These are different layers. Let's say for example this is one layer, this is the same material, this is the same material, and in between you have a different material altogether, and you have a many number of layers, many number of such layers. Let's say, for example, you have 100 layers of these systems. Once you make a system with these many layers, these many number of layers, and to be noted, each of these layers is very thin. Okay, how thin we are talking about? We are talking about, let's say, the thickness of the order of electron wavelength. Okay, you might have studied in this that when do the quantum confinement effects come into picture? When the dimensions become approximately of the order of de Broglie wavelength of the electrons. Okay, so that is what basically you have been taught in this particular course. So that means if you draw the energy band diagram of these particular layers, they look something like this. Okay, they look something like this, and these go so on depending upon how many number of layers. Similarly for the similarly for the valence band, these may look something like this. Okay, and these go on to the number of, depending upon the number of layers. So this is the, let's say, the valence band, this is the conduction band of the of different layers. Okay, and just like this. So now what you have to do, basically you have different energy levels here. This is for the electron, this is for the hole. Similarly here, this is for the electron, holes, electrons, holes, electrons, holes, and electrons, holes. So this is something called as superlattice structure. Superlattice structure. When you have multiple layers just combined together, or I should say deposited one over the another, they give rise to a superlattice structure. It is just like a Why is it called a super lattice? Because it's just like an artificial lattice you have formed. If you talk about a crystal lattice which nature has given us, crystal lattice, the crystal lattice has atoms arranged in a periodic fashion. Okay, that is, and that gives us a crystal potential which looks something like this because of the nuclear potential. The similar way you are making it artificially by depositing one layer over the other, and you form the superlattice structure. Now what happens because of, if you, let's say for example, apply certain bias, let's say a positive here, negative here, all of the bands are going to bend because the electric field is going to be in this direction. So the electric field is going to be in this direction, and you know electric field can be written as minus 1 over q dou the conduction band, the slope of the conduction band with respect to x, or the slope of the valence band with respect to x, basically slope of the energy with respect to the x. Okay, so slope of the energy. Yeah, exactly. So it's going to bend. Okay, so for example, if the electric field is in this direction, you will get a bending like this. If the electric field is in this direction, you will get a bending like this. So this is basically dou E C over dou X. This is basically dou E C over dou X. So accordingly, you get let's say a bending, and you get overall these superlattice layers to be bent like this. Okay, I'm just talking about one of the applications, which is basically lasers. Now, once you have such a bending in the system, what happens is that now you are basically having negative, you are having positive, the electrons are getting injected, and because of clear, I should say, energy levels in these structures, now the energy levels also shift slightly. This is something called as Stark effect, or I won't talk about it, but once you have now the electrons and holes, they can recombine. Even the electron can go here, and then it can again recombine here. The electron can also go into the other level. It can also recombine here. So there's a cascade process of this. Cascade process happens. So once the cascade process happens, it emits, let's say, one photon, then two photons, then three photons, and so on and so forth. And this gives rise to something called as lasing. So it finally emits an intense beam of photons, which are basically in phase with one another. So from the fabrication point of view, there are different perspectives which we need to consider, but this is just the layman overview of how the lasing happens. Okay, so that is why this is just the phenomenon of something called as quantum cascade laser. So it's just like a different layers where in a cascade process of electron hole recombination takes place, and basically there are multiple levels. So the electron comes here, then goes here, then electron can go to other level, then electron can recombine with the hole, and it can give rise to photons. So the cascade process happens, and it gives rise to a lasing. And these lasers are obviously, you know that they are necessary for, let's say, the communication applications. Let's say if you want a laser at 1500 nanometers, what is, let's say, 1.5 microns, which is basically how the internet is working on, what the internet is basically working on. Okay, so there are immense applications, and these are just the few of the applications we are talking about. So now let's say what happens if we talk about the absorption process, because that is what basically we are going to look at. What happens to the absorption? If you talk about the normal semiconductor, you have a conduction band, you have a valence band, and you have a clear-cut band gap. And you say that if the photon energy is greater than the band, greater or equal to band gap, so you have the absorption of the photon taking place. Okay. Now, so for example, if you draw a absorption coefficient, which is in per meter versus the wavelength, let's say for example, this is in micrometer. So what you're going to see is that for a you're going to see a curve something like this. Let's say for an indirect band gap semiconductor, and for a direct band gap semiconductor, you're going to see a step like behavior with respect to the wavelength. So this is for a direct band gap semiconductor. So why that thing happens? This happens because for a direct band gap semiconductor, the photons gets directly absorbed by the electrons and creates the electron hole pair. Okay, and this is governed basically by two things. This is governed by two things. One is the conservation, one is the conservation of energy, and another is the conservation of momentum. Okay, what momentum we are talking about? We're talking about the momentum of the photon. We're talking about the momentum of the electron. Okay, and here we are also talking about the energy of the photon and energy of the electron. So now what happens if we have, let's say, the total energy conservation says that the final energy minus the initial energy should be equivalent to the energy of the photon. So that is basically the energy conservation. And the momentum conservation says that the overall change in the momentum, that means delta, let's say for example, delta P should be basically equivalent to the photon momentum. That means basically h bar k final minus h bar k initial of the electron should be equivalent to h bar k photon. Okay. So this is basically the momentum conservation equation. So this is the energy conservation equation. It turns out that for the indirect band gap, the band gap basically, if you have the momentum conservation is not basically followed in case of the indirect band gap semiconductors. So that is why the absorption is bad there. The absorption is not good, and also there are different processes in indirect band gap semiconductors which compete. So that, let's say for example, if you talk about a silicon, for the silicon, if the photon comes in, then you know that the photon doesn't have the enough momentum to take the electron in this direction. It's not going to go in this direction. The photon is going to go up, then certain intermediate process is going to happen, and then this is going to reach over to this place, which is the conduction band minimum. Okay, let's say for example, a phonon has the ability to take it to the other minimum of the conduction band. So this is like a phonon mediated process. So that's why it's not efficient process. The absorption is not efficient. Okay, later on you will see that at certain energy levels, let's say for example, there are other bands. There is other band. This band is can be extended. There are some more bands in the band structure. Later on you will see that if you go on higher in energy, let's say for example, if you talk about higher photon energies, you will see that certain transitions can take place. Let's say an electron from this to this can go here, electron from this to this can go here. So these are basically happening at some different energies, and these are basically something called as parallel bands. Okay, and they open up certain possibilities of exciting them at higher photon energies. But these happen at very, let's say, huge photon energies, maybe 3 or 4 electron volts. Okay, so now what is this process? This process of absorption is basically controlled by something called as Fermi golden rule. Fermi golden rule basically comes from the quantum mechanics, and it takes into consideration the density of states. It takes into consideration the overlap of wave functions, the wave function, let's say in the final state, and the wave function in the initial state. Let's say you have two states, and this is state initial and this is state final. So the electron can go from here to here, and electron can come back. The wave function of the electron here is psi f. The wave function of electron here is psi I. So that is as simple as that. So now for these two level of systems, you can basically frame some equations which will be governing whether the electron is going to absorb a photon or not. And obviously, it will depend upon how many seats are present here for the electron, which is basically the density of states. Similarly, how many seats are present for the holes, which is basically density of states for holes. This is for the electrons. So that is what we are going to see. So the Fermi golden rule basically gives us the transition probability of, let's say, transition probability of electron from the transition probability of electron to go from state I to state F, some initial state to some final state. And it can be even, let's say, for example, you have initial state like this, and you have some ensemble of states, band of states. Okay, then it can go to some final state here. Okay, It can be a scenario like that. It can be a complicated scenario even. I'm just trying to simplify it. So that is mathematically given by, and you can derive it. We are not showing the derivation part here. You can basically use certain, it's basic quantum mechanics, and you can open any of the things. Let's say, for example, perturbation theory. You can study, and you will arrive at a relation of the Fermi golden rule. If you are interested, you can just look at any of the quantum mechanics book. Let's say Griffith, or for example, you can open. There are there are many good quantum mechanics books. Let's say Applied Quantum Mechanics by I don't remember the name exactly, but you can check the derivation of the Fermi golden rule. So as per this rule, basically it says that the transition probability of going from state initial to final state is basically equivalent to some constant 2 pi by h bar. Let's not worry about it, times the basically some final state Hamiltonian initial state. It's mod psi square. It's mod square into g of e. This is basically the Fermi golden rule. Now here the unknown quantity is this, which is basically something called as matrix element. Why it's called as matrix element, we will see in the upcoming, we will see soon. And this is something which you are familiar with, which is density of states, which is basically number of states per unit energy, per unit energy, per unit volume. So because that is why the density of states has unit number per electron volt per centimeter cube. So this is basically the density of states. So it's just like how many seats are available for the electrons to occupy. Okay, so you are familiar with it. Now the unknown quantity in it is something called as matrix element. So the matrix element you can write basically is basically uh, the final state, Hamiltonian inner state, and initial state, and they are present in some these weird brackets which you call bracket notation. So it's like a Dirac notation. And you know that you can open this Dirac notation. You can open it either, you can write it in integral form. If you are very good at if you are very good in quantum mechanics, you know that you can write it in integral form. You can write it in a matrix form. It depends upon what problem you are dealing with. So in the integral form, you can basically write m equivalent to psi final conjugate as a function of space, the Hamiltonian psi initial dq bar. Basically, it's like a in three-dimensional space. Okay, so this is basically dx, dy, dz. So it's a three-dimensional system. So now what is this basically this Hamiltonian? So Hamiltonian is basically the overall energy of the system. What is basically happening to the energy of the system? So we know that the light is perturbing the system. And what is perturbing? Basically, we're dealing here with electric field. Magnetic field also does, but that mostly, I should say, perturbs the magnetic moment of the electron. Let's not deal about with that right here. We're mostly dealing with the electric field. So you have let's say the electric field, then you have the magnetic field in the electromagnetic wave. This is the magnetic field, which is shown in the black. So we are talking about the electric field component of the electromagnetic wave. Okay, so you know that electric field perturbs the atom, and how it does so? It does so because it has a dot product with the of the dipole moment with that of the electric field gives us the energy. So this P is basically the dipole moment, and it is equivalent to E times the distance, which is the charge times the distance. And let's say if we consider, let's say for example, for simplicity, if we consider light polarized along x direction. That means, for example, if you have a sample with different layers, then the light is basically coming in this particular direction, so that the polarization is along x direction. Along x direction or along y direction. This is the z direction. Okay, so the polarization is along this x direction. So that the electric field oscillations is along this direction. That's what basically I mean. Okay, so once you do this, basically it simplifies maths here. Otherwise, you can just put, instead of x you put y, you get different things. Instead of y you put z, you get different things. You just have to solve the integral, and if you are good at solving the integrals, then it's a cakewalk for you. Okay, so now the perturbing Hamiltonian becomes E times x E naught e to the power I kx. We are only taking the spatial term here right now. We are not dealing with the time dependent part. Okay, so this is the dipole moment. This comes from the basically the electric field of the electromagnetic wave. And now we also have one more thing. We have the electron in the crystal. We have the electron in the crystal system. And one thing you know about the electron in the crystal system, the wave function basically can be represented by some block function, which is the block phase, times some, let's say, amplitude and the periodicity. This comes because of the periodicity. This is because of the periodicity. You know that if you have, let's say, for example, certain atoms in a periodic structure, you can basically have the atomic potential looks like this. I've been showing it from lecture 1 onwards. Okay, so now if you approximate them by a rectangular potential wells, you approximate them vector rectangular potential wells, and you solve the Kronig-Penney model, okay, by taking into consideration the Bloch's theorem. Okay, Bloch's theorem is just the cool trick, a manifestation of that. If you know what is happening to the electron here, you can just know what is happening to here, what is happening to electron here, here, except that you have a phase associated with it. Okay, and you use the concept of periodicity, the repetition of these different atoms. Okay, basically the unit cells. So that is basically what is the Bloch's theorem. And now that this wave function comes because of that. Okay, now what happens is that you have the overall matrix element. Now you can write the overall matrix element to be, let's say, for example, this is final, this is Hamiltonian, this is initial state, and you can write it in integral form as, you can write it as u conjugate x e to the power minus I k final of x. Remember that this is for the electron, this is the electron's wave vector. You can write Ex, this is for the this is the dipole moment, E naught e to the power I k x. This is because of the photon, this is the photon's momentum. Don't just mix up all the k's. And you have one more term which is u of x e to the power I k initial of x into dx. Okay, so this one is again for the electron, because these are the wave functions. This is a wave function part, this is a wave function part, it's complex conjugate. Okay, and this is the perturbing Hamiltonian. Now there is some constant, let's call that constant A, and in this A basically we will absorb all of the constant, let's say the electronic charge, E naught, and other things. So let's write this A. This A contains all of the constants. Okay, and then you solve it basically. You solve it, and what do you integrate it? You integrate it over the unit cell. Okay, when you combine it, let's say for example you combine the exponential parts, you get e to the power I k minus kf minus ki into x u of x into d of x. As you were just talking about the one-dimensional system here, and you integrate it over the unit cell. Now a cool thing happens. This particular term comes into picture. And if you have, let's say, for example, k is not equivalent to kf minus ki. Remember what is k? This k is the photon momentum. This is the photon momentum. Okay. And this is for the electrons. This is electrons momentum in final state and initial state. Okay. So each unit cell gives a different phase. Okay. And when we integrate it over the entire crystal, we can get the, I should say, the momentum conservation can either be satisfied or it cannot be satisfied. So what I mean to say, let's say for example, if this is the condition that the momentum of the photon is not equivalent to the difference in the momentum of initial and final. So when we integrate it over the entire unit cell, we get the matrix element to be equivalent to 0. Okay, that means the momentum conservation is not satisfied. Momentum conservation not satisfied. Okay, so this is one scenario. What is the other scenario? Other scenario is, let's say if k is equivalent to kf minus ki. So the momentum is exactly equivalent to kf minus ki. So because this is, let's say, photon momentum k is equivalent to 0. That means kf is equivalent to ki. So that means kf minus Ki is equivalent to 0. That is what exactly it means. That means M is not equivalent to 0 now, and you have the absorption taking place. So this is basically one of the criteria of how the absorption takes place. So the momentum conservation is really important for absorption to take place. And momentum conservation depends upon whether your initial photon momentum is equivalent to the difference in the momentum of electron between the final and the initial states, okay, or whether it's not. So that is one part. The other part in this equation was in this particular equation was density of states. So the density of states is basically if you have, let's say, let me draw it like this. If you have a density of states, you can write basically the density of states is how many number of energies are present between some energy levels. And if you write, for example, these are like the number of states between E and some small de. Let's say, for example, if you have a K space representation, you have Kx, you have Ky, you have Kz, and you just consider a small dk element and you count the number of the states and then you integrate it. That is what basically how you compute the density of states. Similarly, you can write number of states between k and dk. Okay, basically it's not k and dk, it's k and k plus dk, small element. Similarly, it's e plus de. Okay. So now because the states in both of these has to be similar, that means the g of e, d of e should be equivalent to g of k, d of k, which is basically representing the available states. Okay, so the available states is g of e, d of e, which should be equivalent to that in the k space, just the basic argument. So from the basic analysis, we get this g of k to be equivalent to k square over 2 pi square. So how it comes upon, it basically comes about just like this, uh, 1 over 2 pi by k, 1 over, it's not like this. Let me just show you. It's exactly equal to 1 over lx, 1 over ly, 1 over ly. So you can write it as 1 over 2 pi by k. It's something like that. I mean, you can just check the derivation of these density of states in some of the books. Okay, so you can write g of e now to be equivalent to g of k, d of k divided by d of e, so that you get some, let's say for example, g of k, d of k divided by d of e, and you have a two factor because of the spin of the electron. You can have either up spin, you can have either down spin, and you can obtain this dk over de can be obtained because you know e is equal to h bar square k square divided by twice m. So you differentiate it, you get de over dk, and you take the reciprocal, you get dk over de, and that you can use here. Okay, so you get the ge. Once you do it, you get g of e to be directly proportional to some constant times the square root of e. So that is what you get as the density of states. Now, how does it come into picture in the absorption? So that means the absorption is directly going to be proportional to some square root of E minus EC. Why does this EC come into picture? Because it has to be referenced with respect to some energy level. Okay. For example, if you draw the absorption versus the energy, what energy this is photon energy. Don't confuse it with electron energy. So this is photon energy in electron volt. You get an absorption as like this, where this is basically the some EC, conduction band energy. This basically says that all of the photon energies below this conduction band energy are not going to be absorbed, and all of those energies which are above this particular conduction band energy are going to be absorbed, and they increase exponentially. Okay, so sorry, they increase in a square root fashion. So that means if the absorption coefficient is approximately E minus EC for all H nu greater than EG, and it's approximately 0 for all H nu less than EG. So that is the fundamental notion of the absorption coefficient. Now, there is one more thing. There is for example, we talked about a good thing that you have absorption coefficient, you have the photon energy, and you can have a relation like, for example, it can go like this. Okay. Now, what is going to happen is that you can have certain effects, something called as excitonic effects in semiconductors. Now, what is an exciton? Exciton is like a electron hole pair which does not dissociate. It just acts like a atom in itself. So if you have a conduction band, if you have a valence band, and if you have photon coming in, it generates an electron hole pair. But because of certain Coulombic interactions, because of negative charge and positive, I should say, consideration of positive charge of the hole, there are Coulombic forces. So you know the Coulomb force is given by some minus K Q1 Q2 by R square. Okay. Here Q1 is equivalent to Q2 is equivalent to some electronic charge because the charge of electron in the holes is similar except that there is a sign difference. So you can write it as E square divided by 4 pi epsilon R square, which is basically the force. So this will be the Coulombic force between the electron and the hole. Okay, so there is Coulombic interaction between these bound electron and the holes. That means this acts like a bound system. That's why it's sometimes called as pseudo hydrogen-like species. It's sometimes called as pseudo hydrogen-like species because it acts like a because the hydrogen has a single proton and it has a single electron. So that is how it similarly acts. It has a hole and it has an electron. So it acts like a bound system now. So now the electron and the hole pairs are like moving like a together. Okay, under the application of force even they move together instead of going in the opposite direction. So that is the weird thing. And these are excited electrons. Okay, because these comes from the excited electrons, so that's why these are like excited electrons. So that's how the name comes excitons. Okay, excited electrons. So now what these electrons have a specialty is that they now have a dipole moment associated with them. Because when you separate, when does the dipole moment come into picture? If you separate two charges by certain distance, you have a dipole moment. Okay, so the dipole moment is now, let's say, E times the x. You have the dipole moment coming into picture. And because of that, you have the energy change now. The energy change because of this excitonic effects. Because of, let's say, something called as exciton binding energy. Exciton binding energy. What is this exciton binding energy? If you know the force, you can compute the exciton binding energy quite easily. You know that the energy can be written as some integral of f dot dx. You know f, let's say from x1 to x2. You know force, which is basically e square over 4 pi epsilon r square. Let's say dr. You convert dr, you write it in the form of a r, and you are writing it basically in the terms of the spherical system. And what you can write it as, you can write it as 4 pi epsilon integral of 1 over r square into dr. You can write it as e square over 4 pi epsilon. You can integrate this thing. What do you get? You get minus 1 over r, I guess, and you get minus e square over 4 pi epsilon r as the energy, which is basically the binding energy of the exciton. So this energy has to be included in the total Hamiltonian. Now, and that is why it basically now shifts the absorption edge. Initially, if the absorption edge looked like this, now the absorption edge may look something like this. So this additional effect is because of the excitons. Now you have to consider the binding energy of the excitons as well because it has now a dipole moment associated with it. And you know if the dipole moment is associated with it, that can be added into the total Hamiltonian. And there is exciton binding energy associated with it, which is equivalent to this particular quantity. And now overall energy or the overall Hamiltonian has to have this particular quantity in it. So now the overall picture is going to change. So that's why there's a certain shift in the absorption edge associated with these particular excitonic effects. So this particular excitonic binding energy, it's mostly represented as Rx, and it's in milli electron volt. This is the same thing as EB, the exciton binding energy I represented here. Okay, so it's mostly in milli electron volt. So what does it mean? So that means if even if the energy of the photons is less than the band gap energy, we can have photon absorbed. Okay. Now, because that is what basically opening up this area means. Now you can have photon absorption in this particular area, even if the energy is less than the energy of the photon is less than the band gap energy. So that is what basically this means. That means overall energy is basically the band gap energy minus the Rx over some n square. This is just like a hydrogen atom type problem. Okay, and this is the Rx is here the binding energy. Okay, so it's almost like the hydrogen atom species, wherein you have different energy levels and you write it as minus 13.6 eV divided by n square, where this n is n equals to 1, n equals to 2, so on and so forth for the hydrogen problem, for the hydrogen atom problem. So this is the relation between these. So now these excitons can basically manifest as different peaks in the absorption spectra. They can give you different types of peaks, and they can also be extracted mostly at low temperatures because these energies involved are in the order of milli electron volt. So that's why it's mostly suitable to do the low temperature measurements so that you can get a glimpse of this particular change in the energy values. Usually, because if they are, for example, if the exciton binding energy or what you call it Rx is of the order of, let's say, 20 milli electron volt, then you're not going to see it at room temperature. You're not going to observe at room temperature. Why is that so? Because the room temperature energy is itself 26 milli electron volt, which is basically the volt equivalent of the temperature. It comes because of kT. This is the if you use temperature to be equivalent to 300 Kelvin, you get 26 milli electron volt. That is already the energy, the thermal energy present at the room temperature. So this you can see that the if the room temperature energy is much greater than the binding energy, you're not going to observe the excitonic effects. You're not going to observe excitonic effects. Okay, so that is the fundamental thing. That's why you need to go to the lower temperature so that you can have at least the variation of 20 milli electron volt that can be visible. So that if you go to a temperature, let's say for example 10 Kelvin or 5 Kelvin, then you can see certain variations which is of this order, 20 milli electron volt or 10 milli electron volts. Okay, so that is the fundamental thing. Now, what else we have here? Let's say, for example, we talk about optical gain in semiconductors. Optical gain is simple. We have already talked about it. Optical gain in semiconductors. It is just like, for example, it's the opposite of the absorption. Okay, so if you have an absorption versus the photon energy, just like this curve. If you have a curve like this, which is represents absorption, so it's directly proportional to some h nu minus eg, okay, square root. Then if you draw the opposite curve, this will represent basically gain. So gain is basically minus negative of absorption, so you can write it as negative of h nu minus eg square root. So that's as simple as that. That means, for example, if you have a system, if you have a conduction band, if you have a conduction band edge like this, and if you have a valence band edge like this, you have electrons, you have photon coming in, and if you have electron hole pairs generated. So that means the photon is basically absorbed. Okay, so you have the absorption of the photon. Now, if you have a certain system wherein you have a conduction band already filled, okay, now you have for example, here empty states. If you bring in some source of light, that can basically cause transition of these electrons downwards. It can give off light. Okay, so that is what basically luminescence is even. And this is something called as stimulated emission. Stimulated emission. You are stimulating the emission. If you stimulate it and you bring all of the electrons down by certain, let's say, pump source, let's say it can be a light source, it can be an electric source, okay, then you can get gain out from the system. That means in this case, in the absorption, if the electromagnetic wave is coming like this, it will get absorbed and you will get an electromagnetic wave amplitude falling like this. exponentially decaying. But in this case, if you have electromagnetic wave coming like this, note that this is a different electromagnetic wave. It's not a pump, it's a different electromagnetic wave. Let's say this is an input signal. It's just like a transistor. It's just like a transistor. You have a source, you have a drain, and you have a dielectric, and you have a gate. You want to amplify a signal. Okay, where does the source or the power source of amplification come from? So to amplify the signal, you need some power source. Okay, you cannot just amplify the signal out of thin air. That power source is basically some supply, and that supply is basically sometimes you represent it as VDD. Okay, if you draw this transistor as just like this, you connect here VDD, which is basically some power source, DC power source, and then you connect your signal here, this which is like a sinusoidal AC signal, and okay, and then you get the output at this particular terminal, which is basically an amplified version. But where does this source or the power to amplify the signal come from? It comes from VDD. Similarly, this pump here, it acts like a VDD. It acts like a source. Okay, this here is like an input AC signal, and the output you get is an amplified one, is an amplified signal. So it increases exponentially as e to the power some alpha x. This is basically e to the power minus alpha x, and this one is e to the power alpha x, and it is basically amplifying. Now, how does this amplification sustain? That's a different story altogether, and that is what also that happens in lasing, or that is the process of optical amplification. Amplification, amplification. Okay, so that's it. That's about it. Now, what basically happens in case of in if for example, if we talk about there's a concept behind it. Why does this happen? Let's say for example, if we talk about some semiconductors in general, semiconductor under some equilibrium and non-equilibrium scenario. If you have an equilibrium scenario, and if you have a highly non-equilibrium scenario. So in equilibrium, you know that the law of mass action holds. That means n dot p is equivalent to ni square. This is the law of mass action. Okay, so that means if you have a conduction band, if you have a valence band, you have a intrinsic semiconductor. What we're talking about intrinsic semiconductor. So you can have intrinsic level, which is basically Fermi level here in this case, and you can have a difference between EF minus EI to be equivalent to KT divided by Q ln of N naught divided by intrinsic concentration. You can have EF minus EI to be equivalent to minus KT over Q ln of P naught divided by Ni. So this is basically, I have done some mistake. It's not EF minus EI, this is EF minus EC, this is EF minus EV. Okay, so you know these can be just written in the form of these equations. Now, in the highly non-equilibrium case, what happens? In the non-equilibrium, you have, let's say for example, you have a semiconductor. Let's say this was earlier an equilibrium, Fermi level was here. Now you shine the light on the semiconductor. Now what does it do? It generates extra electron hole pairs, electrons, holes. Now you no longer have N naught P naught to be equivalent to Ni square. So this is no longer valid. Okay, why? Because now you have the overall electron concentration to be equivalent to background concentration plus some generated concentration. Similarly, holes will be equivalent to some background plus the generated holes, change in the hole concentration. Okay, and because of it, now you have a different scenario altogether. You have a conduction band, you have a valence band. The Fermi level now splits. Okay, now you have a separate Fermi level for the electrons, which is the Fn. You have a separate Fermi level for the holes, which is Fp. And these are called as quasi-Fermi levels. So whenever you have a quasi-Fermi level in a system, it represents highly non-equilibrium system. Okay. So that means you have a huge concentration of electrons here, you have a huge concentration of, let's say, holes here. This is a totally non-equilibrium situation. Okay. So now these electron hole pairs, if once they recombine, they both of the Fermi levels will then combine together and they form a single Fermi level, and it will be back to a usual intrinsic semiconductor. So this will be back to the equilibrium condition. So that is how it basically goes on whenever the light is shined over it. And now if for this case you can write a similar set of equations that the quasi-Fermi level of electron minus the intrinsic level is basically equivalent to kT over Q ln of n divided by Ni. But this n is basically now here n naught plus delta n. This delta n depends upon, let's say, it depends upon generation rate. It depends upon the, let's say, for example, the time constant of the electrons. How much time the recombination time is there for the electron, how much time the electron spends in the conduction band. Is basically the decay rate. Similarly, for the holes, you can write it as Fp minus Ei to be equivalent to Kt over Q. There's a minus sign. P over Ni. So you can write P as P naught plus delta P. So these are the equations in the equilibrium and non-equilibrium. Now, what happens basically is that you have, for example, the these are the bands, and if you have electrons here, highly non-equilibrium situation, then you have a quasi-Fermi level for electrons here. Similarly, if you have, let's say, for example, holes, then you have a quasi-Fermi level for holes. This is a highly non-equilibrium situation. Okay, now what is going to happen is that there, if you bring in some pump light, that is going to cause the stimulated emission of these electrons. They are going to then recombine, but obviously there will be certain excitations back to the band. So what basically is going to happen? The absorption spectra is going to look like this. This is the energy of the photon, let's say in EV. For the gain part, you know that the absorption is negative. It's going to look something like this. But for the absorption part, it's going to look back something like this. So in this part, you will be having gain, which is negative absorption. But in this part, this is going to be a usual absorption, which is some h nu minus Eg square root. Okay, so that is the fundamental notion. And most of the time, people try to improve this for if they want to get light out from the material. If they want gain, they want to improve this particular region. There are ways to improve it. People are working on this. This is basically a hot research problem in most of the research groups that are working on it. Okay, so that means you are getting light out from the material, and this is important, let's say, for a solar cells. This is important for lasers. This is important for all of the sources of light. Sources of light. So that is as important as simple as that. Okay. Now, what happens if you have, let's say, for example, absorption in a low dimensional semiconductor? If we talk about absorption in low dimensional semiconductors. Earlier, for up to this part, this was basically mostly for the bulk semiconductors. That's why we consider the density of states to be around approximately the proportional to the square root of E, just like this. That's why alpha was varying as h nu minus Eg square root. Okay, now what we are going to see is that we are going to see what happens in low dimensional semiconductors. Earlier, you were having so many energy levels in the conduction band, so many energy levels in the valence band. This is for the bulk system. Now, if you go to the, let's say, for example, a discretized system, a low dimensional system, you have discrete energies now. Okay, now those discrete energies give rise to a different energy species. Let's say, for example, earlier, if you have, let's say, for example, gallium arsenide, uh, and if you have, let's say, for example, the band gap of gallium arsenide, if we talk about the bulk material, let's say, for example, it's 1.2 electron volt. But if you make a quantum well out of this gallium arsenide, like this, you will see that the first energy level will be here for the electron, and this is for the electron, this is for the holes. As a result, what's going to happen? This is the intrinsic band gap, but there will be this actual gap present, which is the difference between the first level of electrons and the first level for the holes. That means the overall band gap will be Eg dash will be equivalent to Eg plus delta E confinement. And this delta E confinement comes up because of the confinement of the electrons. Basically, when you solve the Schrodinger equation for this well, Schrodinger, you solve the Schrodinger equation, you get the solutions as, let's say, n square pi square h square divided by 8 m l square. L is the width of this well. Okay, so if you then put n equals to 1, you get E1. You put n equals to 2, you get E2, so on and so forth. And once you draw E1, you see that E1 is above the intrinsic conduction band edge of that. That means it's somewhere, it lies somewhere here. And similarly for the holes, it lies somewhere here, not exactly at the bottom. So it has very various implications. Okay. So that is basically the concept of it. And I told you that when does this confinement come into picture? The confinement comes into picture, the confinement for the, let's say the confinement for the electrons come into picture when the dimensions become approximately of the order of electron wavelength. Basically, it's less or equivalent. How does it come into picture? It just comes from the simple Heisenberg's uncertainty. Let's say, for example, if you have an electron and if you confine it in a delta x region, so that the momentum uncertainty is basically h bar over delta x from the Heisenberg's uncertainty. Then you can write the confinement. The basically the confinement energy will be p squared divided by twice m. That will be basically h bar square, basically delta p square. This is the uncertainty in the energy confinement. This will be h bar square divided by 2m delta x square. You can write h bar square divided by 2m delta square to be greater or equivalent to half of kBt. So we are saying here that when is this particular significant? When this is much greater than the half of the room temperature energy. Room temperature energy. Okay, so you can just shuffle it and you get delta x to be less than h bar over under root of twice m e thermal. And you know this particular thing is basically the de Broglie wavelength. So whenever the dimensions are equivalent to or less than the electron wavelength, you have the confinement effects coming into picture. That means electron now behaves like a wave, no longer behaves like a particle. And you have to solve the basically the Schrodinger equation for it now. So that is how you go from a classical electron to wave nature of electron. Nature of electron. Okay, so what happens? That's why if you, let's say for example, if you drop the temperature, you see more confinement effects. More confinement effects. Because now you are dropping basically the thermal energy, you're dropping kBt. And accordingly, you are going to see the confinement effect stronger and stronger. Now you know about we are just going to we are just going to be very fast now because 1 hour is over. So I'll just try to briefly summarize what are the other things. The other things which are necessary is let's say for example we have talked about uh, quantum. We have talked about particle in a box. You know the particle in a box problem. Particle in a box. I'm not going to cover this thing because this is just like a prerequisite. It's the fundamental thing that if you have a box, let's say we're talking about infinite box, infinite well. So the potential outside is infinite. Inside we consider it as zero. When you solve the Schrodinger equation, you get energy levels like this: n equals to 1, 2, 3, 4. This is n equals to 1, 2, 3, 4. So that the solution looks for the n equals to 1 looks something like this. For n equals to 2, this, 3, this, 4. Let me just like draw it like this. So these are the solutions. These are basically psi square. And accordingly, you can mod psi square them and you get a probability of finding the particle. For the finite well problem, if you have a finite well, you again solve the Schrodinger equation, but in a different fashion. Here you have the boundary conditions for the infinite well. You have the boundary conditions that the electron wave function does not exist outside the well. But for the finite well, there is a finite probability of finding the electron outside the well. The energy levels look something similar. This is n equals to 1, 2, 3, except that the first energy state looks like this, second looks like this, the third looks like this. There is certain probability that electron can be found outside the well, which is basically called as tunneling. Okay, this is the tunneling probability, and this is just the finite well picture. Now, what is basically going to happen? So there are certain things that are basically going to happen. So first of all, we are going to see which transitions are possible. Let's say, for example, a photon comes in. Can this electron arbitrarily go to the third state? Can this electron arbitrarily go to the second state, or can this go to any states? Or is it governed by some rules? It turns out yes, and those rules are basically selection rules. It's just a name, doesn't matter. The name doesn't matter unless and until you know what is the mathematics behind it. So these selection rules basically tells you which of the transitions are possible. Okay. Again, I won't go into the mathematics of it because I hope professor has covered it deeply. There's one problem which we might try to solve it, but I'm going to give you a flavor of it, where basically it comes from. So the which transitions are allowed is basically governed by a matrix element. Matrix element. So if the matrix element comes out to be equal to zero, so those transitions are not allowed. If it comes out to be equivalent to non-zero, so those transitions are allowed. That is the simplest thing. What is this matrix element? I talked about the matrix element. You can write it as, let's say, some final state, Hamiltonian, some initial state. Okay. Now you can write it in integral form. You can write it in a matrix form. Integral form you have seen earlier. I have written the integral form in the above slides. How can you write in a matrix form? You see that psi f is basically psi f Hamiltonian psi initial. So psi f is basically this form, psi initial is basically this form, and then you have a Hamiltonian. So all of these are basically matrices. Like let's say for example, this psi initial is actually, let's say for example, a row vector. It's like a row matrix. This is a square matrix. Those of you who know quantum mechanics, they know the reasons. I'm not going to talk about those again. It's like a square matrix. Let's say for example, 100 cross 100, depending upon what system you're, depending on the system, depending upon what system you are dealing with, whether you are dealing with a 2D chain of atoms, whether you are dealing with 1D chain of atoms, it depends upon the system. Okay. And this is again, this is a column vector. Column vector. Let's say this is like a 1 cross 100 column vector. This is like a 100 cross 1 row vector. So when you multiply these, when you multiply a square matrix with a row vector, you get a row vector which is 100 cross 1. So I'm multiplying this with this. Okay, now you multiply the column vector which is 1 cross 100 with the row vector. What you're going to get? You're going to get a single element. So this can be either 0 or this can be either non-zero. So that is basically the matrix element you evaluate in a vector, in a matrix form. So this is how how you solve it. Because most of the things you write it in a matrix form, you can write it in integral form, no doubt. But if you are good at matrices, you can basically write the Hamiltonian in a matrix form. You can write the wave functions in a matrix form, and you can obtain the matrix element and see whether the certain transitions are possible or not. This is how you do it in our computer. If you want to do it, you can do it also in integral form. You just have to integrate the wave functions. You just have to integrate with respect to the Hamiltonian. You have to bring in the Hamiltonian, and you have to write the dipole moments. You have to write all of those integral functions. Okay. So now what happens is basically, for example, if you have, let me just talk about, if you have two levels, let's say for example, this is n, this is n dash. Okay. Then for example, you can write the wave function here, psi I, this is psi f. Okay, and you can also write Hamiltonian, which is P dot E, which is the comes from the electromagnetic waves interaction with the dipole moment of the electrons. Okay, so you can write it as Ex, E naught, e to the power I k x. Similarly, you can write psi I to be in the form of a blocks wave function. Let's say you write it as some UCR, e to the power I k r. Let me write it as, let's not confuse it. This is, let's say, for example, K initial, and there is some phi n of z. Okay, we are basically separating the parts. We are writing it for a two-dimensional system. That is why For a two-dimensional system, you know that overall wave function in x, y, z can be written as wave function in x, y into wave function in z, because this is quantized in z, quantized. So that's why this is quantized one. And this is like a block function, just like a continuous plane waves, block waves, or a block solution. Okay. Similarly, you can write the psi f to be equivalent to this is psi initial. Let's say let's denote the psi initial as AV UV. Basically, V for valence. It's just like these are like this is like a valence band. This is like a conduction band. Consider like this. Similarly, you can write psi f as AC UCR like e to the power I K F R phi n of z. That means this is basically this is not this is n and this is n dash. Okay, now the notation is clear. So this is n dash, this is n. So that's why this is n, this is n dash. This is conduction band. This is so that's why this is final because this is final. So this is valence band, this is initial state. So that's why this is initial state and this is valence band. Okay, now the notation is clear. It has to be clear so that we avoid any kind of confusion. So when you watch this video over the YouTube, you just have to be careful while writing the equations. So now what is going to happen is that you can basically write the overall dipole moment, which is m to be equivalent to mvc into m n n dash. Okay, so this is the dipole moment between conduction band and valence band. And these are different from the actual because you see that let me just tell you if you have a 2D structure and this is not exactly the conduction band here, this is not a conduction band, this is not a valence band here, this is n and n dash. Let me just not confuse you, I'll draw it in a band form. When you have a 2D structure, because the energy is continuous along x and y and it's discrete along z, so what is going to happen here, you will have normal energy bands just like this, parabolic. But along Z, they are discretized. So you have subbands, n equals to 1, n equals to 2, so on and so forth. So this is the usual h bar square, kx square divided by 2m plus h bar square, ky square divided by 2m. But along Z, it will have like this, n square, pi square, h square divided by 2, h bar square divided by 2m l square. Let's say call it let LZ. Okay, so that will give rise to subbands for n equals to 1, n equals to 2, so on and so forth. Okay, so that is what basically we are talking about here. So now you are having conduction band, similarly you are having valence band, and apart from it you are having subbands, n equals to 1, n equals to 2. So now this is valence band. So now you have the dipole moment of conduction band and valence band, and you have the dipole moment of these subbands. Okay, that's different. That is the actual story. Okay, so that's why you have a dipole moment for the conduction band and valence band. You have a dipole moment for n dash, and n dash is basically these subbands. Let's call it n. Let's call it n dash. Okay, this is for the holes. This is for the electrons. So that is the actual picture. Maybe you might get confused what sir has used in the notation. So this is the exact representation. So you write the dipole moment as this, and when you separate it out, you can write the dipole moment of let's say for example valence band, dipole moment for valence band and conduction band as some constant. This is basically the matrix element of valence band and conduction band. You can write it as UC conjugate x UV into dx dy. This x comes because of dipole moment. Okay, you know it's E times x, E naught, all of the things E naught that they go absorbed, they are absorbed as a constant. So this is basically the valence band and conduction band dipole moment, and they go into the matrix element form. Now for the n dash, You write it as phi n z phi n dash z dz. Okay, so this is basically electron hole overlap integral. Okay, so now that means if you have, for example, and here the important thing is we are only considering the polarization along x direction. Let's say, for example, you have a sample like this and you have different layers. That means this is the z direction. That means the growth direction. That means we are considering the electromagnetic wave coming to be here. The electromagnetic wave's Pointing vector is in z direction, but its oscillation is in x direction. This is the electric field uh, electric field component, which is the electric field direction along the x. It can be along the x or along the y. So that is the consideration we are making up here. That means otherwise, if for example you have electric field along z direction, then the electromagnetic wave will be coming out from here, so that the electric field polarization direction is in z direction and its propagation is along x direction. So this would have been a different consequence. Then in that case, you cannot write x at this particular place. We are only considering the polarization of electric field along x direction. So that is the important thing here. Once we do it, we get basically m n dash to be equivalent to. Now you have this is the wave function in n, this is the wave function in n dash. So you know about it. If you have a 2D system, you know about what is the wave function in, let's say, n, and what is the wave function in n dash. Okay, so now if you know what are the wave functions in two different subbands, let's say these subbands, 1, 2, 3, you can just compute m and n dash, which is basically this integral, which is basically UCR star UVR dx dy. You can compute this integral, and you are able to compute basically the matrix element of it. Okay, so this will be obviously zero if n is, if for example for the 2D case, if you talk about for the 2D case, you have the wave functions to be of the form some square root of L sine of n pi x divided by L. So you can write basically this as mn dash to be equivalent to sine of n pi z divided, we're talking about z direction here, pardon me, divided by lz sine of n dash pi z divided by lz dz. And this thing, it will be equivalent to 0 if n is not equivalent to n dash, and it won't be equivalent to 0. That means it will be some finite number if n is equivalent to n dash. So these are the governing selection rules you need to take into consideration. Now I talked about what happens if m equals to 0 or if m is equivalent to finite. Now what is basically going to happen? For example, if you have a quantum well, and if you have electrons energy like this, you have holes energy like this, there's one-on-one correspondence. That means only these holes can go into this one first level. The electrons here can go into the electrons there and producing a hole at the bottom level. Similarly, this electron can go up to this and creating a hole here. That means this is one-on-one correspondence. That means, for example, here the delta n should be equivalent to 0. That means n dash minus n should be equivalent to 0. Okay? If that is the case, then only these transitions are possible. Now, what happens if this is like a inter-band transition. Now, if there is something like intrabands, like between different subbands. Okay, electron going from here to here, or electron going from here to here, whether it's possible or not. For example, we have a n equals to 1, n equals to 2, 3. This is n equals to 1, 2, 3. We are only talking about the electrons, let's say, going from here to here, whether this is possible. It depends upon basically the overlap integral. What is the overlap integral? Overlap integral is psi final, psi initial, dx. Now you need to solve it. And for example, if the electron is going from let's say E, electron is going from E1 to E2, that means this to this level. We can compute it. We can write it as sine of 2 pi, let's say, let me write it as z, sine of 2 pi z divided by Lz, sine of pi z divided by Lz into dz. Okay, there is x. Okay, no, I guess we have made a mistake. So we can write it as sine of 2 pi x over L into x into sine of pi x over L into dx. So you can solve this integral. So you can solve it graphically and you will get an overlapping region like this with a non-zero area. So area under the curve is not zero, hence it is allowed transition. This is the simplest logical explanation mathematically. If you get this integral to be equivalent to zero, then that transition is not possible. And it mostly happens if you have odd, I should say, if the difference, that means, let's say, for example, if there is a transition from E1 to E3, then the difference is basically n, what should I say, n1 minus n3 is basically even, and this transition won't be possible. Okay, so this is a forbidden transition. Similarly, if you have n1 minus n2, it will give you odd number. That means 1 minus 2, which is basically 1. So you get an odd number. So this transition is allowed. So it directly follows from solving these overlap integrals. So this is just like a trick now we follow. So all of those conditions which give you a even combination, they are basically forbidden. All of those which give you an odd combination, they are basically allowed. And it directly comes because of there are sign terms present here. And if you multiply these two sign functions along with the dipole element, you get a function. Then you need to compute the overlap integral. You need to compute the area under the curve. Accordingly, you can compute whether it can be zero or whether it will be non-zero. That's as simple as that. Now, let's move on to the assignment problems. Okay, so we have half an hour left. Now, the assignment problem should be the cakewalk. If we talk about semiconductor devices in various dimensions, we need to match the density of the states, which we have shown that you can write density of states GD to be equivalent to GK dk. You can write then density of states in E to be equivalent to GK dk over dE. GK you can find out, and d over this dk over d you can find out because you know E is equal to h bar square k square divided by 2m. Similarly, doing this exercise for, let's say, 1D, 2D, 3D, and 0D systems, you can obtain the corresponding density of the states. And how do they look like? For example, we talked about the 3D. There, it's the density of state is directly proportional to the square root of energy. For 2D, it's independent of the energy. That means it's constant. For 1D, it's inversely proportional to square root of energy. And for this, it's like a impulse function as a function of energy. So if we draw density of states, let me draw the density of states. Let's say for different cases. Let's say if we have a density of state on this axis and this is energy axis, this is 3D, this is 2D, this is 1D, this is 0D. For 3D system, it would look something like this, which is square root of V function. For the 2D system, it would look something like this, which is a constant of E, constant function. Just like here, it's basically constant, and then it goes to different subband, and then it goes to different subband. This is basically subband 1, this is subband 2, this is subband 3. Okay, otherwise it's constant. And notice that there is a sharp edge and it has shifted from the actual edge or actual band edge. Okay, this is because of confinement. Okay, when you solve the Schrodinger for 2D, you get the first level to be just slightly above the band edge. That is because of the confinement. For the 1D, you get a basically inverse relation for the density of state. This is inverse square root of relation. And for the 0D, you get exactly like a impulse. You get like this is like an impulse exactly. So you have only the states present at that particular energy level, a single energy level. So this is basically, so for the 2D case, you have density of states to be constant. For the 1D case, you have density of states to be inversely proportional to square root of E. So the correct option should be, I should say, for A it's 2, for B it's 3. For A it's 2, for B it's 3. It should be this particular option. Okay. Now, for the second question, the absorption coefficient is shown on the y-axis for four semiconductors as a function of wavelength. Observe that the absorption coefficient for indium phosphide and gallium arsenide shows steep increase. Okay, in alpha near their band edge, whereas for the silicon germanium, it shows a gradual increase. Which of the following is true? Okay, I told you that if you have a absorption edge which is showing a gradual increase or decrease, compared to that, if you have a another absorption edge which is sharp, so this is mostly a feature of a direct band gap semiconductor, and the gradual one is basically a feature of an indirect band gap semiconductor. Okay, so now we have to see which is correct. Silicon and germanium are direct band gap. You can see that for the silicon and germanium, it's a gradual reduction in the band edge, while for the, let's say, for the indium phosphide, it's a sharp drop in the absorption edge. That means gallium arsenide, uh, indium phosphide and gallium arsenide, they are they're direct band gap semiconductors, and the germanium and silicon are indirect band gap semiconductors. So we have to see which of the options is correct. Silicon, germanium are direct, that's wrong. These are indirect and this is direct. So this is the exact answer of this question. Okay. And direct indirect band gap I have discussed a lot in the previous slides. So in reference to the above figure, which material can be used to fabricate photodetectors at the wavelength of this? Okay, so photodetector, obviously it has to detect photons. At what wavelength? It's given as 1.55 microns. So that means if you have a photons coming in, it should be able to efficiently generate the electron hole pairs. Electron hole pair should be efficiently generated. And then you have to basically, these electrons basically get converted into current or voltage that can be read by some, let's say, some sensor or something that can be used for sensing applications. That's what photodetectors basically do, even in your camera or any other thing. So what is the essential thing for it? And basically we have to show it we have to see it in the reference to the above figure. So this figure. So first of all, if you see, we are given this wavelength 1.55 micron. That means the incoming photons should get absorbed at 1.55 microns. Only when they get absorbed, they will be able to generate electron hole pairs. And only when electron hole pairs are generated, they will be able to flow as a current or voltage. Then only we can measure the current or the voltage. Otherwise, it's not possible. Otherwise, let's say, for example, if there is no absorption at 1.55, the incoming photon will just get transmitted through it, and you won't be having electron hole pairs. Okay, so that means there should be absorption at that particular wavelength. And let's say, for example, 1.5 micron comes up here, and there is only one system which is showing the absorption edge, that is germanium. That is having the absorption edge at 1.5 micrometer. That means there will be some huge absorption at this particular wavelength, and it will be able to generate the electron hole pairs. Others are not even having any absorption edge. That means anything that is going to go through it, they will be simply just transmitted through the. Let's say, for example, if you make an indium phosphide based photodetector, any incoming photon will get transmitted or reflected depending upon the properties. Similarly, if you have a gallium arsenide based system, any incoming photon will get transmitted. But if you have a germanium based, it will get absorbed and it will generate electron hole pairs. That will be a very cool photodetector. Okay, so only germanium is the correct option. So now the figure below depicts an infinite quantum well with the electron wave functions for the 5 different energy levels. The transition from lower to higher energy levels for 3 different absorptions are based on the selection rules. What are the allowed transitions? I told you which transitions are allowed. in for an electron to go to a different subbands, only those where delta n, if it's odd, then the transition is allowed. If it's even, then the transitions are not allowed. And it's based on basically wave function overlap. Wave function overlap integral. So psi f times, let's say for example, the x, which basically comes from the dipole moment, psi initial times dx. This integral has to be solved, and it can be either zero, it can be non-zero. If it is zero, then it's not possible, or if it's non-zero, then those transitions are possible. And it turns out, for an infinite quantum well, you have the psi f and psi s as a sine function, n pi x divided by L. This is also sine of n pi x over L. Now you just need to solve it, and you just need to consider when is the delta n. That means, for example, if we consider E1 transition to E3 transition, that means E1 to E3 transition. That means 3 minus 1, which is 2, which is even. So this transition is not possible. Similarly, E3 to E4 transition. That means 4 minus 3, it gives 1. That means it's odd. That means this transition is possible. That means this transition, which is shown here in red, this is possible. What about the green one? The green one here is E3 to E5. That means 5 minus 3 is 2. That means again this is even, so this transition is again not possible. So that is as per the selection rule. And if you want to understand why physically this is happening, then there is a deeper physical explanation for it. And if you are interested, we can go into that depth. If you can just ask me that next time, we can go into the physical explanation of it. This is just what I'm showing you mathematically as per the selection rules. Okay, so which transition was possible? E3 to E4. So only B transition where delta n is odd is possible. So that is the answer of this question. Again, directly comes from the wave function overlap integral, solving the wave function overlap integral. Okay, and the graph below shows the absorption coefficient versus photon energy for gallium arsenide. Identify which curve corresponds to bulk material, which corresponds to the quantum well. Okay, so we have to differentiate which corresponds to bulk, which corresponds to quantum well. So we have to differentiate which one is 3D and which one is, let's say, 2D. So first of all, we see that for the gallium arsenide, this varies as approximately as h nu minus Eg square root, where if you just extrapolate this line, then this point is going to give you the band gap. That means there will be 1.40 electron volt is the band gap of gallium arsenide. So you know this particular relation follows for 3D. But on the other hand, you have the other curve, which is this one, the red one. And for the red one, you are seeing that there are some peaks, n equals to 1, n equals to 2. And once you see these peaks, you also see that the difference between this peak and this peak is smaller than the difference between this peak and the other peak. That is the fundamental picture or the fundamental property of a states in a quantum well. You have distinct peaks, distinct subband states. Okay, so this is for a 2D system. Okay, and you see that this particular edge has shifted from 1.4 towards this end. This is because of confinement. So that's why the overall band gap is now Eg plus delta E confinement. Okay, so what we have to answer. So the curve A corresponds to bulk, curve B corresponds to quantum well. This is the answer. And we also have to, I guess, estimate the band gap of gallium arsenide. I know I told you that how to estimate band gap, just extrapolate it, fit it with a straight line, you get the band gap as 1.4 eV. As simple as that. Okay, now what else? Given below are two statements regarding properties of 2D and 1D materials. That means you have a quantum well, you have a, let's say, a nanowire. So peak carrier density is available at band edge of 2D and 1D material. That is true. What is this basically? Let me show you. So if we talk about 3D, 2D, 1D materials and 0D materials. And if you talk about the density of states, what we showed in the first slide itself, for this you showed the density of states varies as square root of E. Let's say square root of E minus EC. This is some energy value EC. For this, the density of states varies as it's like a constant. It's like a constant, but slightly shifted from the band edge. That means it's like this. These are for different subbands, subband 1, 2, so on and so forth. For 1D system, it is just like uh, inversely proportional to the square root of E minus EC. If there is some energy at this particular point with respect to certain energy, E. And for the 0D system, it is a step, sorry, an impulse function. Now, you also have Fermi distribution. And you know this Fermi distribution is basically it's not it's not a quantum mechanical entity per se. It basically comes from thermodynamics. It's like 1 over 1 plus e to the power e minus e f for some reference level divided by kt. That is basically a Fermi function, and it just tells you the probability of finding an electron. And when you see the derivation of it, it comes from the purely the thermodynamics aspects, not the quantum mechanical aspects. That's why you see the Fermi function. It is similar at non-zero temperatures, similar for all these at T not equivalent to 0 Kelvin. Because at T 0 Kelvin, it's exactly like a step. So this is Fermi function. So this is with respect to E. So this is like electrons energy, not the photons energy. Just don't confuse the electrons and photon energy. So now what you have again, now you know that if you have density of states, if you multiply it with Fermi function, you get carrier density as a function of E. But if you integrate it with some energy level E1 to E2, if you integrate these functions with respect to dE, you get N, the number of electrons basically. And it will no longer be a function of E because you're integrating it with respect to E. So you just have to understand what I basically say. So that's why you can draw N of E. And how do you draw it? You just have to multiply these two. You just have to multiply the density of states, just like multiplying density of states with the Fermi function. Similarly here, multiplying, let's say for example, let's say density of states with the Fermi function, multiplying density of states with the Fermi function. Let me draw it like this. The Fermi function, density of states, okay, just use the same color. So this is density of states, and then you have the Fermi function. So when you multiply it, you see that there is an overlapping area, which is this thing. So this is basically the carrier density, n as a function of E. This is n as a function of E. This is n as a function of E. And this is n as a function of E. You see, there is a sharp carrier density at, I should say, band edge. In what? It's also sharp here, it's sharp here, it's sharp here. But here it's not sharp. There is some width associated with it in 3D. So that's what basically this thing is particularly saying. The carrier density sharp in case of 2D, 1D, and 0D, but it's not sharp in case of 3D. So that means if you have a 3D system with a conduction band and valence band like this, and the if you draw its what you call as the if you draw its carrier density, that will look something like this. For the electron, this is N of E. For the holes, it will look something like this, P of E. That means there's a peak. It's peaking at around. It's not exactly peaking at the band edge. It's peaking at a higher energy value than that of the band edge. We're talking about 3D. But for the 2D, the great thing about 2D is if you have for 2D, if you have these sub bands, the band the N of E exactly peaks at the band edge. Let me not draw right by this. It exactly peaks at band edge. Similarly, P of E peaks at band edge. And it has its implications, okay, in terms of how the excitations take place, what kind of energies get absorbed, because it's going to impact the absorption of the photons as well. Similarly for the 1D and the 0D systems. So another thing is S2 statement, it says excitonic absorption is visible in 2D and 1D materials. That is also true. Okay, why is it true? Because, for example, if we talk about excitonic absorption, we say, for example, if you have edge like this, then you can have excitonic absorption that can make absorption possible for photons less than Eg. Okay, and it becomes possible for the excitonic absorption becomes highly possible in 2D and 1D systems. Why is that the case? It is basically related to exciton binding energy also. Okay, if you remember the previous relation, we saw the exciton binding energy is it's related to something like 1 over A, where this A is basically the something called as Bohr radius. I guess this is A square. I don't exactly remember, but we can derive it. Just this, I don't like to remember, just derive it. F is 1 over 4 pi epsilon q square divided by r square. So then we can write energy to be F dot dr. This is 1 over 4 pi epsilon q square, 1 over r square dr. So this will be 1 over 4 pi epsilon q square, 1 over r. Uh, let's not talk about signs here right now. 4 pi epsilon r. This is binding energy. That means the binding energy is the electronic charge square 4 pi epsilon r. So that means if you go on reducing the r, the exciton binding energy increases. Okay, so if that increases, that is going to impact this particular energy shift, and it will be visible in lower dimensional systems, because in lower dimensional systems you are reducing the overall size, overall r. Something called as, I guess this is called as Bohr radius or something. I guess it's called as Bohr radius. Bohr radius. So if you reduce the r, the exciton binding energy is going to increase, and it's going to be visible as a different absorption edge in case of 2D, 1D systems, basically lower dimensional systems. Okay, so I hope that is basically the explanation of it. Yeah, it sounds logical. If you have any doubt, then you can just contact me. So this is basically the correct statement. So these are true, and this is the correct explanation for S1 and S2. Okay. So now another one, the question 8 is basically it's like a cakewalk. Consider an infinite one-dimensional potential well. So this is 10 nanometers. The effective masses of electrons is given at T equals to 300 Kelvin. Energies of first and fourth levels, that means 1, 2, 3, 4. So this is fourth level. So we have to compute E1 and we have to compute E4. So I just leave it to you as a problem, because you just have to solve E1 as pi square h bar square divided by 2m L square, because n is equivalent to 1 here. So for E4 you can write it as n square, which will be 16 pi square h bar square divided by 2m L square. You just have to replace m as 0.1 into 9.1 into 10 to the power minus 31 kgs. You have to replace L as 10 into 10 to the power minus 9 meters, and then you can compute it. And it's a cakewalk. I guess you will be able to do it. And the solution of this particular problem is this particular thing here. Okay. That's it. And if we talk about question 9, the figure below shows experimentally determined absorption coefficients. These are the absorption coefficients for different thicknesses of gallium arsenide. And we have to choose the correct option in regard to the thickness. You see that what is happening, this is almost like this is a single peak here. It can be because of excitonic effect. Otherwise, it's like a continuous full bulk-like system, bulk-like behavior, something like h nu minus eg square root behavior, except this peak. And these here are subbands. And you see that these are like this is like a confinement has taken into place, taken effect, and this is like subbands like these. So the distance, or I shouldn't say distance, the energy difference between the subbands is going on increasing. So that is why if you are that means if you're going from LD to LC, the size is reducing. From LC to LB, again the size is reducing. And that can also be seen because the band edge is basically shifting. You see, this is shifting towards the higher energies. And why is it shifting? Because if you have, for example, for the bulk, if you have absorption edge along at this point, if you confine it, if you confine it in a well, your energy will be shifted. Let's say, for example, if you lower this system's dimension, let's say, for example, a well, quantum well, now you have the absorption at this particular value, uh, this particular value, which is shifted. Okay, so this is for different subbands. Now, if you again reduce the dimensions of the well, for example, if you have one well like this is one well, and this is another well, and this is another well. So you see, for this energy level will be here, for this energy level will be here, for this, no, I'm exactly not showing it correct. Let me just draw it. So for this energy level will be here, the energy level will be here, and the energy level will be here. So this goes on increasing with respect to the bottom edge. So that is why there's a shift in this particular point here. Okay, it's just a property of the energy wells. So if you go on widening the quantum well, the energy level will be exactly present at near the band edge. But if you go on making it thinner and thinner, the energy level is going to be going higher and higher and higher. Okay, with respect to the bottom edge. That's as per if you just solve it, you are just able to visualize these systems. So that means if you also can visualize it, that means for LD is greater in size than LC, then LB, then LA. So this should be the answer of this question. Again, these peaks, multiple peaks can be because of excitonic effects. Okay. So why do you think there are two peaks corresponding to each quantized levels n? What two peaks are he talking about? Okay. Hmm. Okay, so there are two peaks. He's okay. This is not because of excitonic. This one can be because of excitonic effect, or this can be not exactly because of excitonic effect. It can also be because of something called as heavy hole to conduction band transition and light hole to conduction band transition. So basically, what happens if you talk about this is like a conduction band, this is like a valence band, but you have one more band like this, and then you have another band. If you talk about, let's say, for example, a material called gallium nitride, you have a single conduction band, but you have a heavy hole band, you have a light hole band, and you have crystal, I should say, split off band. This is called a split off band. Okay, and basically it depends upon the curvature. If you see the curvature, that is different. And what does the curvature indicate? It indicates the effective mass. Effective mass of what? Effective mass of holes. So effective mass of holes or electrons. You can write the effective mass in general basically as h bar square divided by dou square e over dou k square, which this basically represents the curvature. So the effective mass is inversely proportional to the curvature of the bands. That is from the basic device physics. So more the curvature, less the effective mass. So that is why this is lighter and this is heavier. Now there can be possibility that the transitions can take place from a electron going from this to this. That means HH to conduction band transition. Electron can go from this to this. That means LH to conduction band transition. And because of slight energy difference between these two bands, it's of the order of milli electron volts, I guess. They will manifest as different peaks in the spectra. The just like these peaks shown here, just like these peaks, these two peaks shown here, this one, this one. Similarly, the other peaks. Okay, so that is basically the transition of these electrons from heavy hole to conduction band and light hole to conduction band bands. There can also be some transition from here to here, but that is a very different story altogether. How does this split of band come into picture? And I guess there is even in presence of magnetic field, you can just play with these bands, but that is also again a different story altogether. You can play with the spins. You can have different combinations altogether. So the solution of this is from HH to CB, LH to CB transitions of the corresponding quantized subbands. Yeah, that is the exact answer of this question. So here we are basically talking about if you have a subbands like this, then you have subbands of the holes. So you can have heavy hole, light hole, and this is conduction band. Okay, so that's why you see if most of the times when you draw the conduction band, you draw it like this, but when you draw the valence band, you draw it like just like the curvature is different than that of the conduction band. The reason is because this is for the hole, this is for the electron, and the curvature itself is basically signifying the effective mass, and that's why the curvature for this one is also different. So that's why this one is heavy hole and this one is light hole, because this is more curved. And what does the curvature mean? It's basically dou square E over dou K square. And how does it affect the effective mass? You just have to go back to how you basically define or how you understand the effective mass concept. Okay? Just you can just brush up those concepts again, and you will be able to understand why these curvatures determine the effective mass of the electrons. Okay, just like you remember if you have, let's say for example, if you have one band like this, and if this is E versus K, then you can basically, from the slope of this E versus K, which is dE over dK, you can compute the velocity. So the velocity is basically, the group velocity is basically 1 over h bar dou, 1 over h bar dou E over dou K. So if you differentiate it, you get the velocity of the electron, the group velocity of the electron. So when you differentiate it, let's say if you differentiate it, there'll be maximum peak here, the slope here is 0, there is maximum peak here. So you get something like this, and you get something like this. You get something like this. This is the group velocity of the electrons in a band I'm talking about. So it reaches maximum at certain point, and it goes to it kind of goes back and forth in this band. That is the behavior of the electron. And again, if you draw the effective mass of this electron in a band, basically it would look something like this. So this is m star. M star is inversely proportional to 1 over dou square E over dou K square. So this is the exact representation. Okay, so that comes from the semiconductor physics you have studied already. Okay, so that's it for today. I guess we have discussed a lot of stuff, and I've tried to cover everything, whatever the professor has taught in this week. And I hope you are kind of looking at these lectures. And you can these sessions are basically just like a revision sessions as well as the question and answer solving sessions, whatever you have studied in the entire week. So if you just see these lectures, see this particular 2 hour lecture, your entire week will be almost covered, and you'll be able to solve the problems. Okay, so that's it from my side for today. I hope we will meet next time. Till then, bye bye.